Hello students, welcome back. Let's resume our discussions on exponential and logarithmic functions. We talked about all those definitions. Now let's talk about exponential and logarithmic rules. Exponential rules. We have these special exponents. 0 power is 1. First power is itself. Negative first power is its reciprocal, 1 over a. And 1 to whatever power is always 1 because, repeated multiplication of division by 1 is always the same. Well, those are basically the remarks. First three are basically definitions. Repeated multiplication to 1, and 1 times no multiplication of a, so stays in 1. And 1 times 1 multiplication of a, so it's a. And then 1 times 1 division of a, because this is negative, so it inverse. And then the last statement, 1 to whatever power is 1, that works really well for, any integer for rational numbers. Repeated multiplication of 1, repeated division by 1, and radical of 1. They're all 1s, no problem there. And then the statement is not so simple for irrational numbers, however, and even worse, for complex numbers, it actually fails. Let's see, do we have something more? Oh, never mind, too complicated. Just stick to your common sense. 1 to whatever power is 1. Now, exponential rules for the same base. A to the x power times a to the y power is a to the x plus y power. So repeated multiplication of x times, another y times, so total x plus y times of multiplication. Division, then that's the inverse, so subtract. And then a to the x power times y power, then you multiply by the powers. Let's see, do we have some sort of proofs or semi-proof? Okay, all right. When we have integer powers or positive integer powers, we get repeated multiplications like this, x times y times, so total x plus y times. It's easy to see, right? And then the third one, a to the x power, another a to the x power, another a to the x to the power. That whole thing is repeated y times. And then each a to the x power is x times, another x times, another x times, and total y times. So x times y times, I'm multiplying by a. Make sense? Okay. Relatively easy to understand when x and y are positive integers or non-negative integers. And then how about the middle rule? That's a little bit trickier because you'll have to consider the repeated division. If there are more in the numerator than the denominator, x minus y times, we have a numerator. You see, x times says 15 times, and then divide 10 times. So what's remaining? 5 times. And then in y is bigger than here, 10 times, and then divide by 15 times. And how many left? 5 times of these. So y minus x power, but then again, that's x minus y power, because, we are flipping over, taking reciprocal. A bit harder to understand, but you see, eventually we are reversing this operation. Division is inverse of multiplication, and then subtraction is inverse of addition. When they're negative integers, then you'll simply take reciprocals. And then if they are rational numbers, okay, those are tricky. And you can actually prove these things like this, but I don't know how many of you are interested in these kind of proofs. I take a little bit more detailed viewpoints for STEM algebra and also STEM calculus. But here, well, everybody has to remember the end result, of course. And of course, to remember the end result, some kind of reasoning like these in terms of repeated multiplication will be helpful. Okay, next. What if you have same power and different bases? I can distribute those powers, either multiplication or division. How does it work? They're actually much easier to see. You see, ab to the x power, ab times ab times ab times, that's repeated x times, but change the order of multiplication. A to the x power here, b to the x power like that. Make sense? And then the same thing goes for the division. A over b times a over b times a over b times, and so on. Total x times, you see. And then numerator, a to the x power. Denominator, b is multiplied x times. So we have a to the x power over b to the x power. Excuse me, here's a typo. Sorry about that. Should be same x power. You see, same power. Sorry about that. That was just a typo. When x is negative, then you can do the same thing to the denominator. Yeah. And then for rational, it's going to be tricky. We have to deal with those radicals, but in the end, it works out. A bit tedious, but okay. But in the end, everybody has to remember the end result. Different bases with same power, we distribute those powers, okay? And different powers with same bases, well then, multiplication becomes addition, division becomes subtraction, and then repeated power of power, becomes multiplying the power. Okay, remember those, and let's go to logarithmic rules. That's basically the inverse. First rule, cancellation rules. All right. Log and exponential cancel each other out because they're inverse of each other. Again, the same thing. And special case, we talked about it. This actually is a to the 0 power. So canceling a and then this log of a, we get this power back. So log of 1 is 0. Let's see, is there reasoning behind it? Oh, okay, all right. Special case, when a is e, then we have natural exponential. So instead of log base a, we have ln. Otherwise the same. Proof? Oh, never mind. I'd emphasize a little bit more if this had been STEM algebra or STEM calculus, but not too much. I don't want to overdo it. All right, next, log rules. Standard rules. Log rule changes multiplication to addition, division to subtraction, and power comes out as coefficient. Well, let's see, what about the exponential rules? When you have the same base, yeah, they're all about the same base A. Multiplication becomes addition in power, division becomes subtraction in power, and power of power, we multiply the powers. So that's, third one is a little bit harder to see with some connection with this one, but the other two are easy to understand. It's the inverse. Multiplication becomes addition, multiplication becomes addition, and the division becomes subtraction, division becomes subtraction. Power, that's a little bit different. And then if you actually want to prove this, as a matter of fact, you can do these. A to the x power, y power, like these. Too complicated? Okay, all right, then never mind. You can prove the second rule like this. Understand? Great. But if you don't, oh, then never mind, just skip. Same goes to third one. If you understand, great, but if you don't, then never mind. In any case, please note that the exponent rule, a to the x power to the k power, is a to the kx power. That is actually being used. So these three rules correspond to those three rules of exponent rules for same basis. Special case, when the base is e, then we use ln instead of log. Again, the same deal. Multiplication becomes addition, subtraction becomes, division becomes subtraction, and k power comes out as coefficient. Warning, addition is not like that, and then multiplication does not go backward, all right? Log of xy is this, log of x plus log of y, not log of x times log of y, all right? And then this log of x plus log of y is log of x times y, not log of x plus y. Nonetheless, I see these errors a lot. especially the first one. This one relatively rare, but this one I see a lot. There goes some warning. And then let's see, do we have some more? Okay, change of base rules, all right. A to the x power can be rewritten as e to the x times log of a, and log a of x can be written as natural log of x over natural log of a. So base downstairs goes downstairs. The reason is kind of like this. E to the x to the log of a, I can get this coefficient up to the power. Need a little bit bigger font. Get this coefficient x up to the power, and then what do you see? Exponential and log cancel each other out when we have a to the x power. That's a proof of this guy. And then as for this one, well, you can do it like this. Log a of x is from here I'm taking the log. Oh, that's too hard. Okay, never mind about the second part. From here, basically I'm taking the logarithm. That's how you get the second rule. No, that's too hard. Remember the results though. A to the x power can be changed into exponential like this, and then arbitrary logarithm can be changed into natural logarithm like this. And this one may be a bit awkward, but this one is easy to remember. A is down here, so a goes down. X is up here, x goes up. And then this used to be a useful way to calculate the arbitrary logarithm with your calculator. Because your calculator supports natural logarithm or special log base 10. So you can change base. For example, if you have to calculate log base 3 of, say, 17 with your calculator, then that's natural log of 17 over natural log of 3. And you can calculate these. You can get a certain digit string over another digit string, and we can work this out. Yeah, never mind about the proof. The first one is not too bad. The second one is a bit complicated. Okay, we went through the exponential and logarithmic functions. I hope that was a good review. In business algebra or STEM algebra or some other algebra classes, we took one entire week or more, I think, in this section 1 alone. But I'm spending about 20 minutes or so to cover everything, so I ran quickly. But I hope it was okay.